Hello Calc 3, welcome back to the last video scheduled for May 13th. In this video we will be covering the second part of section 12.4, just a few applications of the cross product. I do want to say before I begin that I think after this video is done we will have about an hour and a half of videos scheduled for May 13th, just one day, which is certainly more than is to be expected. So I just want to let you know that typically you are not going to have to watch videos this long. It just so happens that at the beginning of the semester we have multiple sections to cover per day, and that kind of necessarily makes the videos long. Once we get into chapter 14, 15, and 16, where we're only covering one section every day, you shouldn't need to spend more than about 40 minutes per day just watching me talk about stuff. Okay, so let's move into an application of the cross product. We're going to start with an application to physics, specifically torque. So remember that for the dot product we had an application to work, which is a concept inside of physics. The cross product will have an application for torque. So look at the diagram that I have conveniently taken from the book down here. So when we turn the bolt by applying a force to the wrench in the diagram, we produce a torque that causes the bolt to rotate. And the torque is going to push the bolt, I guess if you had the bolt in a wall, it would push the bolt into the wall. So notice that the torque vector, the vector in red in the diagram, is directed along the axis of the screw, and it's in the direction consistent with the right-hand rule. So what exactly do I mean by that? What I mean is that if you take your right hand and you point your fingers in the direction of the vector r in the diagram there, which is the vector connecting the pivot point to the point at which the force is being applied on the wrench. So point your fingers in that direction, and now I want you to curl your fingers down towards the force vector. Then your thumb should end up pointing in the direction of the torque vector in red. And this means that the torque vector satisfies the right-hand rule or is consistent with the right-hand rule. And the magnitude of the torque on the bolt is defined, this is a definition here, it's defined to be the magnitude of our vector r, which is the vector connecting the pivot point to the point where the force is being applied, times the magnitude of our force vector times sine of theta, where theta is defined as the angle between our force vector and r. And notice that the direction of the torque is the same as the direction of the cross product of r and f. And for this reason, the torque vector, which is often denoted tau, is given by the magnitude of r times the magnitude of f times sine theta. So this gives the magnitude of tau. And then our direction is going to be the normal vector, n here. And of course, this is the definition of the cross product. So our torque vector is actually equal to the cross product of the vector r and the vector f. So let's move into an example where we use some numbers here. So assume that we have this blue bar that I have drawn in the diagram over here. And the left-hand side of the bar is going to be the point P, the right-hand side of the bar will be the point Q, and the bar is 3 feet long. And P is a pivot point, so the bar is going to pivot around P. And there is a force being applied at Q on the bar, which is represented by the vector F, and that forms a 70-degree angle with the vector from P to Q. So assume that our force vector, or the magnitude of our force vector, is 20 pounds. We want to find the magnitude of the torque at our pivot point P. Well, we just found out that the magnitude of the torque, which I call tau here, is equal to the magnitude of the cross product between our vector PQ and our force vector F. And that will be equal to the magnitude of PQ times the magnitude of F times the sine of the angle between them. And now just plugging in some values, we end up with 3 times 20 times the sine of 70 degrees, which is equal to 60 times the sine of 70 degrees. And then you can just plug that into a calculator, and you find out that the torque is equal to about 56.4 foot-pounds, where foot-pounds is the unit for torque here. So we are now going to introduce another kind of vector product, just composing the cross product and the dot product that we already have. We're going to call this product the triple scalar product, or sometimes it's also called the box product. And it is defined to be the product of 3 vectors where you have u cross product with v, and then that resultant vector dot producted with the vector w. So this is going to be the triple scalar product of u, v, and w, u cross v dot w. Okay, so let's see what we can figure out about this triple scalar product. So first we're going to worry about the magnitude of the triple scalar product. So just considering the fact that u cross v is a vector and we're taking the dot product of u cross v with w, we know that the magnitude is going to be equal to the magnitude of u cross v. Remember, that's just a vector, so we're just dot producting 2 vectors here, times the magnitude of the vector w times the absolute value of cosine theta, where theta is going to be the angle between u cross v and the vector w. And as I already said, this is just using a fact that we already know about the dot product. So u dot v is equal to the magnitude of u times the magnitude of v times cosine theta. So now let's give a geometric interpretation of the triple scalar product. So geometrically, the magnitude of the triple scalar product actually gives us the volume of a parallelepiped. If you don't know what a parallelepiped is, it is the shape that I have in the picture here, which again I've conveniently taken from the book. You can think about it as a 3-dimensional generalization of a parallelogram. So the base of the parallelepiped is a parallelogram. It's the parallelogram formed by the vectors u and v. And we already said that the area of that parallelogram is equal to the magnitude of the cross product of u and v. So that's something that we talked about in the previous video. That was our geometric interpretation of the magnitude of the cross product. It's the area of the parallelogram formed by u and v. The height of the parallelepiped that we have in the picture here, which I've denoted h, is given by the magnitude of w times cosine of theta, where theta is again given in the picture here. So notice that theta is the angle between the vector w and the cross product of u and v. So just using a little bit of trigonometry, we find out that the height is equal to the magnitude of w times the absolute value of the cosine of theta, where again theta is the angle between w and u cross v. So the volume of a parallelepiped is given by the area of the base, in this case the parallelogram formed by u and v, multiplied by the height of the parallelepiped, or h, as I have drawn in the picture. But as we just discussed, the area of the base is equal to the magnitude of u cross v, and the height is equal to the magnitude of w times the absolute value of cosine theta. And now we can conclude that the volume of the parallelepiped is actually given by the magnitude of our triple scalar product, so U cross V dot W. And there is another way to evaluate the triple scalar product using determinants. And in this big purple section here, I just derive this new formula, but again, I don't think that I should probably go through it in this video. It'll be in my lecture notes that I post online if you want to look through it, or I think the book talks about it as well. So instead of going through that, I'll go right to the formula that we get for calculating the triple scalar product as a determinant. So if I have three vectors, u, v, and w, and I want their triple scalar product, which is u cross v dot w, that is equivalent to the determinant of the matrix that I have written here. So the matrix where the first row is the components of u, the second row is the components of v, and the third row is the components of w. And finally, let's just give an example where we find the volume of a parallelepiped. In this case, it's determined by these three vectors, u, v, and w, that I have given below. So we just said that the volume of the parallelepiped is equivalent to the magnitude of the triple scalar product. But the triple scalar product is given by the determinant of the matrix where the first row is the components of u, the second row is the components of v, the third row is the components of w. So now let's just plug in some numbers. So our first row of our matrix will be 1, 2, -1, using the components from u. The second row will be -2, 0, 3, again using the components from v. And the third row will be 0, 7, -4, using the components from w. And now we want to calculate the determinant of that matrix. So we're going to expand along the top row, along 1, 2, -1. And we get a 1 times the determinant of the 2 by 2 matrix 0, 3, 7, -4, -2 times the determinant of the matrix -2, 3, 0, -4. And then lastly, we get a -1, which is this term up here, multiplied by the 2 by 2 matrix -2, 0, and 0, 7 for the second row in that matrix. And now let's calculate the determinants of these 2 by 2 matrices that are appearing. So first we have 1 times 0 -4 minus 3 times 7. That'll give us a 0 -21. Then we have a -2 times the determinant of our second 2 by 2 matrix, which is -2 times -4, giving us an 8, minus 0 times 3, which is of course 0. And then for the last matrix here, the last 2 by 2 matrix, we have a -1 that we're bringing down, times the determinant of that 2 by 2 matrix, which is -2 times 7, minus 0 times 0, which again is of course 0. And we end up with this -14 minus 0 being our determinant. And now we can add all of these numbers together. We end up finding that the determinant of that matrix is -23. And the volume of the parallelepiped is going to equal the absolute value of the triple scalar product, which ends up being 23. So that should be a nice example of a calculation. I think you might have a calculation to do similar to this in your homework. It's definitely something that you just get used to with practice. So that is the end of the content for section 12.4 and also the content for May 13th. So keep a lookout for section 12.5, which we will cover on May 14th.